Okay, off we go. Here's where we were last time. We were talking about surface integrals, and we developed the idea of a surface integral, kind of an analogy to how we developed the idea of a line integral. And then we tried to apply this idea to a particular circumstance, namely flux. Seemed like a reasonable thing to try to compute with a scalar surface integral. It ended up being importantly different, right? We have this key distinction that flux, you have to have an oriented surface to make any sense out of it. Otherwise, plus, minus, who knows, right? I mean, there's a real problem there. So we ended up with this importantly different idea, and thus a new kind of expression. And by going through this calculation, we end up with our new kind of integral, a vector surface integral. Very analogous, by the way, to when we developed work, right? We looked at, again, a physical scenario, this idea of the amount of work it takes to move along a curve. And we went through a computation and ended up with a new kind of integral. So vector line integrals and vector surface integrals they come about in analogous ways, applied to, of course, different geometric and physical scenarios. Okay, so, and then furthermore, I guess I did that too soon. Furthermore, we had already developed everything we needed about parametrization of surfaces to do the pullback. Just like over here, we had already developed everything we needed about parametrization of curves to do the pullback. And this is about where we left off last time. Let's see here. Okay, right. No, wrong button. Yeah, here we go. So this is about where we left off last time. We had done this pullback. We had plugged in the stretching factor part of the pullback, which is really the only thing that isn't just plugging stuff in, and gotten to a nice formula, parametrized formula. Everything in this formula is computed from the parametrization. In other words, pulling back through the parametrization. Everything is in the ST plane. That's just a good old-fashioned double integral, and something that we can totally compute. Okay, now before we actually do I think this is where we ended last time. I do want to remind you, there is this looming concern here of what is the math crime that got committed here. And again, I'm sweeping that under the rug for the moment. I don't want to get too distracted by little subtleties. It is going to be important, and we've got enough going on as it is right now. So let's kind of sweep this under the rug for the moment. We will come back, but it might be entertaining for y'all to think about. Okay, wait a minute. What is wrong with this claim that that's equal to that? What is the shortcoming there? Okay. All right. So, example. Question is to compute the flux. You'll notice here that when it comes time to doing the calculation, that's the very first thing I write down is our brand new formula for how to compute flux, pulling back through a parametrization. We have a vector field given. Cool. We have a surface given. Fine. The surface is a graph. So because it's a graph, I am allowed, and in this case inclined, to use the graph parameterization. There it is. Right? We talked about graph parameterizations previously. We take the partials, and then we take the cross product to get to our capital N vector, which, of course, is the thing that we need to plug into our formula. So there we go, just plugging in the capital N vector. All right? How are we doing so far? More to say, of course, but is everybody on board so far? All right, so now what's going on with the vector field there? That looks weird, right? I mean, the formula for the vector field is this. How did that turn into this? That's not immediately clear. Don't forget, when you look at the coordinate variables x, y, and z, right? Those coordinate variables, those are literally the outputs from the parameterization. They are literally X, Y, Z. You see right there, they are the outputs from the parameterization. So said differently, the parameterization itself gives you the formula for x, y, and z. It's very easy to lose track of this, which is why I'm emphasizing it. But notice, everything works out if you just keep that in mind. So for example, here is my formula for x, right there. X goes right there, and so to the question of how do I rewrite this second coordinate of the field vector, well, it's x squared, but wait, x is s, and so x squared becomes s squared. Right? And then likewise, likewise with the t becomes y. Right? And then likewise with z. So that z, that's the formula for z. It goes right there where that z is, and that ends up telling me how to compute the first coordinate of the field vector, and that's why the first coordinate of the field vector ends up being that. How we doing? Is everybody okay? Notice it's just plugging in, right? But you got to keep track of what is determined where. Okay. All right. Moving along, let's take a look. Oh, let's see. Let's think about the bounds. We got to think about the bounds for the integral. So this integral I have going from 0 to 1 and 0 to 1. Where'd that come from? How do I know that? Well, those are supposed to be values of s and t. So let's think for a moment. What do I know about s and t? Well, the first thing I observe, very conveniently, s and t are x and y. I mean, they're literally the formulas for x and y. So when I ask what the range of values of s and t, ranges of values of s and t are, I'm asking what the ranges of values of x and y are. So I need to look at my surface and think about, okay, well, what's the range of values of x and y? And it says right here, we're looking above the unit square. That's pretty much literally telling me, because I'm using the graph parameterization, that x and y range over the unit square. And the unit square is 0 to 1 and 0 to 1. Does that make sense? Everybody happy with that? Okay. All right. Okay, so it's kind of all over but the shouting at this point. This is literally a double integral. Okay, sure, you gotta, multiply out that dot product, but this is an easy double integral over an easy domain with a polynomial integrand. I'm gonna call that actually a pretty easy integral. Yeah, there's some details. There's gonna be some annoying fractions, right? But it's pretty simple. Okay. Okay, now again, I have committed a math crime. Right? And, well, oh my gosh, if this is in fact not perfectly mathematically valid, then, whoa, is this example valid? Well, it turns out that it is. So the crime that I committed did not rear its ugly head in this example. This example went through just fine. We got the right answer. Everything on the page is valid. Arguably, I overstepped a point that I should have considered, but everything ended up being right. Okay, so what is this problem? And the problem has to do with how we parameterize. And roughly speaking, you have to parameterize the correct direction. Now let me remind you, when we were talking about vector line integrals, we were talking about parameterizing curves. We're talking about computing work, for example. And if there's a mountain road and you have to drive that mountain road, well, it's a very different experience driving uphill as opposed to driving downhill. So when you parameterize, you have to parameterize the correct direction. If you've been asked to drive uphill, and if you parameterize downhill, you're going to get the wrong answer. You're going to be off by a minus sign. In other words, you're going to get a terribly wrong value. So we actually have the same issue here. It's harder to see it coming. When you parameterize a curve, the direction that the parameterization goes is usually kind of obvious, right? It's the whole idea of a parameterization is that you're literally tracing it out. We visualize a parameterization as being the process of drawing the curve And when you draw something, you can watch your pencil tip move in a direction, right? So the orientation is usually kind of clear. Not so with surface parameterizations, right? When we parameterize a surface, I've parameterized, but then I got to compute the various partials. Then I got to compute the cross product of those partials, and only then can I look at the unit vector that defines the orientation of how I parameterize it. The orientation requires some work to identify, right? So that's why it doesn't leap off the page as much, and that's why we didn't really notice, because we just kind of feel like we're just kind of covering the points, and it's sneaky that we are in fact picking we are parameterizing in a direction. Implicitly, in this case, of course, which direction through the surface. So what we have to keep in mind is that this is not just kind of free up for grabs, right? We were given an oriented surface. We were given a surface where, let me use the darker green. We were given a surface where the orientation is supposed to be a certain way. And okay, sometimes, right, about half the time, the orientation unit normal and the parameterized unit normal are the same. And sometimes you get lucky, and it's a coin flip, right? Sometimes you do, in fact, get lucky and you parameterize the correct direction unwittingly, right? Can't take credit for it, right? But cool, everything's fine in that case. And if this is the case, then yes, we parameterize the correct direction. Everything's fine. Okay, but of course, it might have been that the surface was parameterized the other way. And if this is the case, the n that we use to describe the required, the orientation that was given that describes the actual surface we're interested in, and the unit normal that describes how we have arbitrarily parameterized it are not the same, right? And if they're not the same, then you can't do algebra with them as if they're the same. So this is exactly what went wrong when I committed my little math crime here, right? So I'm going to flesh this out in a little bit more detail, but this conflated the two possibly different unit normals. So here's that fleshed out a little bit more. Now here's that same little bit of algebra. There's that math crime, right? And the concern that we have for whether this is valid. And let's just think about what we got here. Where did this normal vector come from? That normal vector right there came from the fact that we've been asked specifically to compute the flux in a specific direction through the surface. Namely, it was given. It's part of the definition of the surface we want. What about, now don't forget, yes indeed, we can rewrite the capital N, like so, like I have there. But what can I say about this unit normal vector? Where'd that come from? That unit normal vector came from capital N, which came from a cross product, which came from partials, which came from the parameterization. So this is not necessarily the same, right? So when I claim, hey, looks like a duck, quacks like a duck, not really, right? I have little n times the magnitude of capital. That little n might not actually point in the same direction as the little n that I want to claim it is. That's the problem, right? The green orientation unit normal and the blue parameterized unit normal, coin flip, might be different. Cannot claim them to be the same. How we doing? Everybody see the problem? All right, now, okay, so let's worry about that a little bit. Let's look back to this example. Oh my gosh, did I blow it? I mean, is my capital N vector pointing the opposite of the direction it's supposed to? We legitimately need to worry about that here. Let's see here. It says I'm supposed to orient upward. That means I want my orientation unit normal to be upward. That means if I want to be able to pull this pullback thing, my parameterized unit normal had better point upward as required. And it does. You can see right there in the formula, there's my formula for capital N. The z coordinate is positive. It might not be pointing exactly upward. Of course, obviously, I mean, this is not a flat surface, right? Every surface is going to point, maybe somewhat upward. Right? The normals will point maybe somewhat upward, but I mean, you can't expect it would be literally exactly upward. But certainly, this vector does not in any sense point downward. Right? As far as the orientation goes, as far as distinguishing between my two options of which way to go through the surface, this is the one that, of course, we would call upward, not downward. So, we got lucky, and as I said, everything's fine with this example, but honestly, I really should have recognized that yes, indeed, my arbitrary, pulled out of thin air, made up parameterization, actually is, going the correct direction as it's supposed to be. Okay, now, what if it hadn't? Right, we got lucky on that example. What if we get unlucky? Which again will be about half the time. Right? And how do you deal with that? Do you have to re-parameterize all over again? And fingers crossed, hope you get lucky the second time. Maybe have to do it a third time. No, not at all. All you have to do is just recognize, whoopsie, my normal vector is pointing exactly the wrong direction. That means every term in my integral is exactly the negative of what it's supposed to be. And, okay, cool, just fix it. Just multiply by -1, right? Just like with line integrals. Remember we talked about this with line integrals. If you parameterize a curve backwards, maybe it's easier. Maybe you've already done it. Whatever, if your parameterization is backwards, it's not that big a deal. Just recognize that you parameterized it backwards. Fix it by multiplying by -1 at the appropriate time. And proceed. No problem at all. And so that's what we're going to do here. And real quick final reference. This orientation is the only thing that we have to worry about. Any two parameterizations that have the same orientation will give you the same value. So again, we don't have to worry too much about the parameterization, just how is it oriented. Okay, so here we go. Next example. You're going to notice this example to be very similar to the first example. Same surface, same vector field. Computing the flux. Practically the same, right? The only difference is that this time the surface is described explicitly as being downward. Right, so I want to compute the flux downward, said definitely the surface is oriented downward. Again, not straight, literally exactly straight down. Obviously, the only surface that could literally be oriented exactly straight down is a flat plane. That's clearly not what we're talking about here. So downward is just a tool for distinguishing between the two options. It's unambiguous in that distinction. We'll talk more about the language in a couple of minutes here. But okay, so I'm supposed to parameterize this downward. Now let's proceed as we do. Our surface is a graph, so we're going to use the graph parameterization. And then we play the usual game. We take the partials and we take the cross product, and that gives me my normal vector. And all of what I've done so far is all just kind of naively, blindly proceeding as if there's nothing to worry about, and I think that's fine. And I encourage you to do this. Just parameterize any which way. Don't worry about it. compute the capital N by all the formulas that we have. Fine. Don't worry about it. But then you have to pause. Right? You got to pause and ask, okay, there is an orientation visible in this capital N vector. My parametrized orientation. I can see it right there in that capital N vector. I also know what I was supposed to have done because that's given in the statement of the question. And so when you get to your capital N vector, that's when you absolutely have to pause. You got to wait a second and say, whoa, I parameterized arbitrarily. I was making stuff up. I might have parameterized this the wrong way. I might have parameterized it upside down, you might call it. And so you got to do a check. And you got to ask yourself, wait a minute, downward? Is that downward? And no, it is not. How we doing so far? Anybody on board? So we parameterized it the wrong way. Again, now, does that mean that I have to scrap all of this work and start over with a different parameterization? No, not at all. No, we parameterized it backwards. Let's just recognize that and say, whoopsie, we're going to fix it with a -1, and you just stick in your minus and proceed with your calculation. No problem. Everybody see how that works? Everybody buy it? Now, one thing I want to emphasize. It's your responsibility as the person doing the computation to check and make sure that you've parameterized the correct direction. It's not going to be signaled in the statement of the question. This is something that you have to know. It's part of the process of computing with this pullback formula. So don't look for any reminders on this. And so you have to make the mental note. You have to have a little mental, stick it note. Anytime once you get to your capital N vector, whoa, hey, slow down, pause. Did I do this right? Or am I off by a minus sign? And then react appropriately. Okay, now I do want to emphasize that this is arguably me being a little fussy, but I think this is really important. Where do you put the minus sign? I claim that this is the correct place to put the minus sign in this case. And let me explain why. Let's think about the orientations of what we are looking at here. So we've been asked flux. Flux is oriented according to however the question is stated. Right? Flux is a result of, the given orientation. What about this? Which way is that oriented? Well, ds vector is the orientation unit normal times the ds scalar. So this too is oriented according to how the question is stated. Okay. What about this? What's the orientation implicit in that calculation? Well, the capital N, the parameterization. The orientation that comes from that blue expression is not automatically tied to the statement of the question. It is not automatically the given orientation that we're supposed to use. So this comes from the parameterization. Obviously, so does that, and et cetera, as you compute. So you've got to put the minus sign where it belongs, right? So if I put the minus sign as I did there, and I've got here, it says that green is the negative of blue. Well, that's right. It is green is the negative of blue. So that's where it needs to go. And then of course it carries along, obviously. But let's entertain now, what if I did the following? What if I say, whoopsie, parameterized the wrong way, I gotta fix it with a -1, and what if I just put that minus sign here? Right? Let's just suppose. Well, what's the problem with this? I'm still gonna get the correct answer at the end of the page. Right? I put the minus sign in a little bit late, but whatever. If all you care about is the answer at the end of the page, then it doesn't matter. but as you all heard me say a million times, and I say it a lot because it's so important, that's not what we're interested in here, right? So this is a class about mathematical reasoning, and as applied to particular things, namely multivariable calculus. But mathematical reasoning is a very important part of what we're interested in. So if you put the minus sign in the wrong place, you've actually made two false statements. For one thing, as written, I seem to be claiming that green equals blue. Oh, no, it does not. They are negatives of each other. That's wrong. This equal sign there is wrong. That's a big deal, right? I'm also saying that these two blue integrals are negatives of each other. Also wrong. Yeah? So we got two false statements on the page, and that's just, you just can't do that, right? So please do pay attention. You gotta understand which of the various things that we write down in this process are oriented how, and then put the minus sign where you actually make the switch. Otherwise, you're writing down nonsense. And again, not good. Okay. All right, how are we doing? Pausing again for questions. Everybody on board with that? All right. Okay. So, let's talk about the language a little bit. And again, it's not going to be exact. We'll say stuff like upward and downward but none of the orientations are literally going to be exactly straight up. Unless, again, of course, what are the odds if you have a completely horizontal plane? I might work out that way, but that's rare and, basically not going to happen in most cases. So how do we use these terms if they aren't right? And the point here is the job of this language is not to be exact. We're going to use equations for that, right? We're going to write down the actual normal vector explicitly, exactly with algebra. So the algebra will nail it perfectly, right? The purpose of the language is not to give an exact description. The purpose of the language is to distinguish unambiguously between the two possible orientations. So for example, let's look at, we got this surface right here. Right? And let's think about the two different orientations that we could talk about. What are the two different directions through that surface? And, well, one of them is like that. There's an orientation. That's a bunch of vectors perpendicular to the surface. You know what? That doesn't show up as well. Let me do this with the pencil. A bunch of vectors perpendicular to the surface. Forgive my poor art. And then now here's the other option, a different collection of vectors all perpendicular to the surface. Like so. And now, suppose I want to be able to conveniently communicate my intentions as to which way I want to compute flux. Do I want to compute the flux as oriented by the green normals or flux as oriented by the blue normals? And, I guess I could write down formulas, but my gosh, what a pain. I'll have to do that eventually, but I kind of want you to do that. I want to just be able to communicate casually and conveniently. And so I claim that these words totally do that. If I say oriented upward, whoops, let me get back into the highlighters. If I say oriented upward, every single one of these green vectors is at least somewhat upward. And not a single one of these blue vectors is in any sense upward. So if I say oriented upward, it's not exactly upward, but it completely, 100% removes any possible legitimate ambiguity between which of these two orientations I might actually be talking about, right? So it does its job perfectly. And likewise downward, right? Downward has to be the blue vectors. All of the blue vectors are at least somewhat downward. None of the green vectors are in any sense downward. So it does its job. Does that make sense? How are we doing? Does everybody see the point here? Right? So the big picture point is that you're going to use language to remove ambiguity between the two options. Just think about what's going to get right to removing that ambiguity as quickly as possible. Now, another thing you could do is you could say inward and outward, right? So inward, oh gosh, I mean, I suppose most people would probably guess that I meant the green orientation if I say the word inward. But just if I wanted to be really quibbly, right, if I want to be really uptight, there isn't technically an inside or an outside. It's not a closed surface. So inward, not actually really removing any ambiguity. It probably, the listener would probably guess correctly, but that's not really good enough. So that's why I put a little sort of, a dissatisfaction symbol there. Okay. All right, now, what if we have a different surface? What if I have this sphere? Well, again, I have two possible orientations. There's that one, and there's that one. And now, upward and downward worked so well previously. Let's entertain the question of whether maybe I can say upward and downward. But it's terrible. It's absolutely unacceptable. If I say upward, right, which one of these two orientations, green or blue, am I talking about? If I say upward, some of the green vectors are upward, some of them are downward. Some of the blue vectors are upward, some of the blue vectors are downward. It doesn't remove the ambiguity at all. So these words are, however great they applied to the previous surface, they're abysmal choices for this second surface. So you got to tailor the language to the geometry. And again, this is part of your job, right? This is something you have to make reasonable choices. And likewise, when someone else has already made the reasonable choices, you have to interpret appropriately. Okay. All right. And likewise for the third example there and other language options. Okay. Moving along. Sometimes you get lucky. By the way, let me remind you, we are still very much on track for here it is. For the patterns that we noticed, there were some digressions there. But when we were doing vector line integrals, right, sometimes you get lucky with geometry. And here we are, likewise with flux. Sometimes you get lucky with geometry. So let's pull on that thread here. And how do I get lucky in the geometry in this case? Now, we have a sphere given. Got the equation given. It's a spherical graph. I can use the spherical graph parameterization. I could totally parameterize this thing and take partials and pull back, blah, blah, blah. I don't want to, though, right? Look at that. I mean, if I parameterize with the spherical graph parameterization, I'm going to have sines and cosines everywhere. X, Y, and Z are all chock full of sines and cosines. Now look at the vector field. Right? Wow, no good. Then think about how am I going to find my capital N vector? Well, I've got to take my parameterization, full of sines and cosines. I've got to take partials. Okay? I've got to do a cross product. It's gonna get a little hairy. Not that it can't be done, but it's not a good way to solve this problem. At least if there's a better option. So here's the better option. And again, you gotta love spheres. Spheres have just wonderfully convenient geometry. If you look at a point on the sphere, and if you look at the given, says right there, outward orientation, and it points like that, perpendicular to the surface, And here's the beautiful thing about spheres. Perpendicular to the surface is always, if you're talking about a sphere centered at the origin, perpendicular to the surface is always parallel to the position vector. We made a similar observation some time ago, back when we were talking about line integrals. Here we're going to use that in a different way. Look what I did. Typo in the notes. My apologies. Typo. I wrote this as the x vector. That is, that's a relic. I made a decision some time ago to change my notational choice. I used to like to use x vector to represent x, y, z. Now I'm using r to represent x, y, z. And I went all the way through the notes and I thought I'd caught them all, but I missed a couple of them apparently. And so anyway, apologies. But this right here should be the r vector, and it's just that's just a typo. So that's r. Okay, so we have this position vector, r, and then the normal vector points in the same direction. But being a unit vector, I have to divide the magnitude by the magnitude of r, namely 3. So, boom, I have a formula for that normal vector. Normal vector is r over 3. You can write that down. Notice I haven't parametrized anything. No sines and cosines, right? Purely just a convenient geometric observation there. And, I haven't done the pullback, and I have no assurance that this integral is going to work out nicely. And, very often it doesn't. But, again, sometimes you get lucky. And notice that in this case, lucky break, this dot product is exactly 0. And so the integral is 0, pen down, walk away, and totally awesome. So like I say, sometimes you get lucky. And you'd be surprised how often stuff like this comes up. The world's full of symmetries. It's super convenient. Right? So this kind of thing, you really should have your always be looking, head on a swivel. Don't get on the blinders and just, I'm going to plug and chug every time. You're going to expose yourself to a whole lot of effort that you didn't need to do. Right? So all you got to do is just look for opportunities. Look for situations where it might be really convenient, like this case here. Look how convenient to write down that normal vector, because we love spheres. Spheres have awesome geometry. Write it down. See if you get lucky. Very often, it does. Okay. What do you think? Pausing again. Everybody all right with this point of view here? All right. Here's another one. Have to squeeze it in a little bit. There we go. Okay, so this is a little bit of a weird surface. Okay, first of all, it's part of this plane. But specifically, it's the part that satisfies that inequality, which, that's, so x can't be very big and z can't be very big. But it looks a lot like the inequality describing a disk, but it's fourth powers instead of squares. And so, it's some vaguely, disk-like thing, but not, right? It's something kind of like that. So there's our actual surface. And notice that we want to compute a flux, right? And here's one of our several ways to compute flux. And notice, I'm not parametrizing. Again, we're about to get lucky again. Point to the luck being that we don't have to parameterize. Okay, so how do we get lucky here? Well, the first observation is that, forget about this fourth powers business. The mere fact that we're talking about part of that plane tells me that my normal vector has got to be that. It was pretty sweet, right? I don't have to parameterize, take partials, do the cross product, right? Then worry about whether I oriented it backwards in the parameterization. I can just say, oh, okay, well, that's a plane perpendicular to the y-axis. The normal vector is going to be in the direction of the y-axis. And in fact, notice it even tells me how to orient this, right? I'm looking for the part of y equals 3, but specifically oriented in the positive y direction. And that's how I know that it points that way, not that way. Does that make sense? Is everybody with? Okay. All right. Cool. So let's see here. Let's go ahead and write that down. Our normal vector is 0, 1, 0, right? And again, hardly any work at all. Okay, now there's still the annoying matter of the vector field, right? And I've got this monster of a vector field that I've got to deal with. Okay, but don't forget, we have, very conveniently, that our entire surface is within this plane, y equals 3. So our entire surface, every single point we're going to plug into this calculation, y is 3. So I'm just going to take that and plug it right into this vector field. That y is 3 and that y is 3, and I guess that's all of them. Anyway, go ahead and plug it on in because the whole plane has that feature. And when I do that, notice that this second field coordinate becomes 0. And thus, I get to put a 0 right there. Now again, no parameterizing. Right? I didn't have to algebraically earn it by, taking a deep breath and plowing through the usual plug and chug formula. Just, careful observation, boom, 0. Right? Everybody happy? Everybody see how that worked? Now, another quick observation, just strategically speaking, when it comes time, when you're taking an exam, again, stuff like this is not going to be labeled. It's not going to be, I'm not going to tell you to be on the lookout for this during the exam. That's part of your job. And likewise, when you get out of this course, right, when you're taking higher level engineering classes or working as an engineer in industry or whatever you end up doing, when you encounter some situation where this little bit of trickery is going to be awesome, no one's going to tell you, right? So you've got to be on the lookout for it. And I want to strongly encourage everybody, channel your inner laziness, right? This is a great time to encourage the laziness of hoping that there is a quick and easy way around the problem, because fairly often there is. And again, I've made some, data-less, approximate assertions as to how often this happened in my experience when I was an undergrad taking classes that involved a lot of integrals, as you will too. And I think about 10% of the integrals that I saw, right? About 20% were 0 by odd symmetry. I think about 10%, something like that. Non-trivial portion, right? Pretty significant portion. Cool stuff like this kicks in and makes stuff go away. And of course now it's all over, but the shouting, the very last little bit here is to observe that the dot product that we have in there is in fact exactly 0, and therefore our integral is 0. Okay, so heads up, right? Always be on the lookout for this kind of thing. Very real world. Okay, now this, I am going to be real quick about this part, coordinate surface integrals. Now again, I hope you all recall when we were talking about line integrals. Again, the very next thing that we did after Lucky Break geometry was we talked about coordinate line integrals, which was basically just an alternative notation that comes about from just writing everything in terms of coordinates. No big deal. It's just a kind of fleshing it out, and there it is. Boom. Right? And pros and cons of this kind of notation, mostly cons, honestly. I mean, in my experience, taking 1 million physics classes, and I think also so your experience in taking 1 million engineering classes. Yeah, it didn't come up that much. Now, when you get into some really high-level math, if you get into some, start doing some, graduate level kind of math or upper undergrad kind of math major type classes, oh, this stuff is awesome. This is the only way to fly for certain kinds of situations, right? So, very good notation, but it's probably not going to affect y'all much, if I had to guess. So anyway, analogous thing here. Same basic idea. We've already established that formula. We've already established N is that formula. And notice all I'm doing is just taking these, writing them in coordinates, and fleshing it out. I'm literally just cranking out that cross product, et cetera, et cetera. And you may recognize that we did, in fact, make a passing reference to this formula for capital N, right? It's kind of weird, and I tried to lure some of y'all to come talk to me about, hey, why is that? Why do we get two-dimensional change of variable stretching factors as coordinates of the capital N vector, right? So, it's very sort of odd and unexpected. It's a real eyebrow raiser. So we didn't really do anything with that observation, but now we are. Now I'm just going to make the observation that if you kind of distribute the ds dt like so, right? And then you look at, for example, this thing. I mean, what do you think we ought to call partial yz partial st times ds dt? Oh my gosh, we've totally seen that before. That's literally stretching factor times input differential, right? Kind of feels like maybe we ought to call that dy dz, just like we did back in chapter 5, right? When we were doing change of variables, dy dz makes total sense. And by the way, in case you're curious, writing dy dz makes it look like we're talking about area in the yz plane and geometric. I got to be really passing about this because 0 times height, etc. But in fact, what we're talking about, the dy dz, keep in mind we're actually talking about a piece of surface in space. That dy dz says project over to the yz plane. Look at the shadow in the yz plane, and that dy dz is representing literally the area in the yz plane. So it actually does make geometric sense. And again, there's a bunch of details we don't have time for. So anyway, likewise there and there, and you take that formula for ds and you plug that in. And don't forget your vector field has coordinates, and again, we typically use PQR, and here we are again, that we can just take this dot product and kind of multiply it out, as if that makes sense. And this is our new alternative notation for a vector surface integral. And again, this is kind of what differential forms look like. If you're curious, it's extremely natural in a sophisticated mathematical sense. It's extremely powerful. You can prove stuff with this notation, well, to be precise, with differential forms, which looks a lot like this notation. You can prove stuff that eluded Gauss his entire life. Right? It is very, very powerful. But again, most of the applications of this don't come up. Why am I showing you? Aside from just kind of cultural, it's good to know, culturally relevant points, you're going to see this. Like it or not, reasonable or not, I would argue that in many cases that you're going to see it, it's going to be pointless, right? But you are going to see stuff like this. And when you do, you need to know what to do with it. And what you do with it is you remember that dy dz, dz dx, and dx dy is just kind of a fancy way of describing the ds vector. And therefore, whatever the coordinates were in front of that is just another way of telling you the vector field whose flux this is supposed to represent. All right, so that part is important. When you see that stuff, you can reinterpret, you can kind of reverse engineer the more natural notation that we have on the left. Okay, and let's see, I think we are in fact out of time. Okay, so perfect place to stop. We'll finish it right there. Y'all have a great weekend. Oh, real quick, I hope y'all noticed, I forgot to mention at the start of the lecture, the website's back. Right, we're back in business. So thankfully, I think everything should be normal. Fingers crossed from here on out. Okay, see y'all later.